Now, so far we have discussed yes, the shear stress and bending stress is induced in a beam as a result of external forces acting over the beam whose line of action is perpendicular to the longitudinal axis of the beam. As a result of this external, as an effect of this presence of these external forces, the beams will got bent in all the different sections in different way, and we have to and whole beam is stressed by tensile and compressive stresses along the longitudinal axis. But at the same time, we also notice that there are vertical forces or shear forces or shear stresses induced in each axis of the each section of the beam itself, other than the bending moment generated due to the summation of external bending moments acting over the beam itself, algebraic sum of the bending moments acting over the beam itself. As a result of bending moment, the bending stress is created in different sections of the beam, and we have discussed what is the constitution of neutral axis, which is nothing but an axis or a plane where there is no bending stresses or shear stresses. Bending stresses either compressive or tensile stress in nature, and it does not change its length or reduce its length due to the action of external loads. Now, initially we have decided that shear stress is too small to be neglected in the stress in understanding the stress scenario of a loaded beam. But later on, we have noticed that there are some important sections or important portion of the beams where the shear stress makes any very important, whose design is dependent greatly on the shear stresses existing created over it. Now, so in order to know that, we have to now find out the effect of the shear stress acting over the beam itself. And by considering a elemental length of the beam, whose elemental section length of the beam between two sections at the distance dx, which is infinitesimally small, we have find out the constitution of bending stresses, constitution of neutral axis. Then we invented point for the calculation of shear stress for a beam with rectangular cross section. Now let us consider what will be the shear stress condition over a beam having a triangular section. Now, here we have a triangular section of the beam whose height is h and whose base is equal to small b, and which is also, we have shown a section over the portion of a beam a, j, k, whose height is equal to x and whose base jk we are supposed to calculate. And we know from our earlier discussion, the shear stresses on a layer, any layer jk, which is away from a distance y from the neutral axis, is given by this formula. Tau is equal to f a into y bar divided by ib, where f is the shear stress already induced in the particular section under consideration, and a into y is the moment of the shaded area above the neutral axis, and I is the moment of inertia of the rectangular section about the triangular section exactly about the neutral axis itself. So we are having these unknowns like shear force of the section, which is actually unknown. First, we have to know this section, know this stress, and then we can do the next of the calculations. Next, we have to find out what is ay, or we have to find out what is a and what is y bar, and it is I is the moment of inertia of the beam that we are supposed to know, and b is the width of the beam, is the underneath here. Now, first we have to find out for this analysis. For this analysis, we are supposed to find out the width of the beam jk, which is given by from the neutral from the similar triangles a, b, and c, and a, j, and k. We have jk divided by b and x divided by h. X is the height of this triangular section with triangular section, and H is the height. X is the height of this triangular section AJK, and H is the height of the full triangle. So thus we got this width B here is Bx into H, where this B is this B, and X is this height, and H is this height. Now let us find out the area of the section itself AJK. We know area of any triangle is equal to half of the length of the base multiplied by the height of the triangle itself. Here that means the area of this section AJK is equal to half JK, which is the base of this section, and X, which is the height of this section. So half Bx by H into X, which I have already calculated Bx by H, which is the base, and which is X is we multiplied by X, and half is out there. Bx squared by 2H is the cross-sectional area of this section AJK. And what is supposed to be the y bar? Y bar, what we have told that in earlier discussion, the y bar is the distance of the CG of this section from the neutral axis itself. So how you will get it? We know that neutral axis generally passes through the center of gravity of a particular section. So here the center of gravity of this full triangular cross section ABC is equal to 2/3 H by 2. But it is to be divided, total H is to be divided by 3 times, and it is to be multiplied by 2 to know the distance of the CG from the point A. So from the point A, this is H 2/3 by H into 2/3 is the distance of CG from A. Similarly, H for the same reason 2x by 3 is the CG of the distance of the section AJK, which is away, whose height is equal to H itself. So the distance between this CG and this is the difference between these two. So 2H by 3 is minus 2x by 3, and 2 by 3 multiplied by H minus X, which is the y bar, or distance of the CG of this section from the neutral axis itself. Now from this equation, we know F, we got A, we get Y dot, we are supposed to get I and B. So A we have received A, and Y bar is given. We put F into A into Y bar divided by I into Bx divided by H, or F divided by 3I into X into H minus X. Achha. So the tau section at a distance y from so the shear stress itself is of what this section is F by 3I into H by H into X minus X squared. Now, it is the equation of the variation chi with respect to X from the top of the triangle is a parabolic in nature. And at a point where x is equal to 0 means the top of the triangle, or x is equal to h means the bottom of the triangle, tau is equal to 0. And at neutral axis, where x is equal to 2a into h by 3, if we put the value of 2h by 3 in s of x in this equation, and if we simplify the matter, this will become 9f h squared by 2f 227f. Now, if we put the 27i, I is the moment of inertia. Now, if we put the value of moment of inertia of a triangle here, which is equal to bh cubed by 36, then this equation will reduce to 8 into f, 3 into b into h. So, tau can be represented by the shear stress acting over this section itself, the width of the beam, width of the base of the triangular beam, and height of the triangular beam. With this thing, this tau 8 into f by 3b into h, this is the equation for the shear stress acting over a triangular section. And if we use the area of the beam itself, which is equal to b into h by 2, half b into h by 2, and put it here, then this equation will take the form 4/3 f divided by area, or 1 into 1.33 to tau average. Now for the maximum intensity, differentiating the equation 2 and equating to 0, d tau by dx is equal to f by 3i. Differentiating the equation and equating to the 0, d tau by dx f by 3i is equal to hx into x square is equal to 0. Again further, again now then it will happen that h into 2x, h minus 2x is equal to 0, x is equal to h by 2. So the maximum value of shear stress will happen at a distance half of the height of the triangle. And if we put these values of x in this earlier equation, we will get tau max f divided by 3i into h by 2 minus h by 2 whole square is equal to f h square by 12 into I, or put the value of I here, then again simplify, it will become 3 into f divided by b into h. This is the maximum shear stress induced at a distance h by 2 away from the top of the rectangular section. Again, we replace this area by b into h by 2, then this equation will take the form 3 by 2 f by area, or equal to 1.5 tau average. So maximum shear stress is equal to 1.5 times or 150 times of average shear stress. The distribution of the shear stress is, I'm just showing you again. This is the distribution of shear stress like this. Here h by 2, here it is tau max, and it is 0 at top, at 0 at bottom. Okay. Sure. Yeah. Now let us go through the distribution of shear stress along a I section. Here we have a I beam whose sectional view is like this, where B is the width of the flange itself, D is the maximum depth of the beam from this end of the flange to this end of the flange, small b is the width of the web, and small d is the depth of the web itself. Let us go through the next portion. 6. Now we know that the shear stress on a layer jk at a distance y from the neutral axis is given by this equation, tau f multiplied by 8 y to the power A y bar divided by I into B. Now, let us consider two important points. When y is greater than d by 2 and when y is less than d by 2, which means what is d by 2 here? From the central line of the section to the beginning of the flange itself. That is d by 2, or from here to here, that is equal to d. So from here to here, it is equal to d by 2. So now if uh, y is greater than d by 2, means when y, we want to consider some section which is lying here in the flange itself, then their treatment will a bit different. When y is less than d by 2, means when we want to know the shear stress condition of a point acting on the wave itself. So first we have to consider what is the distance, what is the shear stress over the flange, and next we will discuss what is the shear stress over the wave itself. Now, what is shown in this diagram is, first of all, here we have this section over the flange itself, that is J and K, and which is away from the wave itself. So the area of this shaded area of this shaded portion will be width B multiplied by the total height h by 2. So here we know that height is the total height from here to here is capital H. Is d by 2 exactly. It is d by 2 because this length to this length is d. So this length to this length is equal to d by 2. Means multiplied by y and minus y, where y is supposed to be somewhere here on this, over this line jk. So the area is this width as well as this thickness of the flange itself, and y bar is equal to y plus half. This is the y, and from here to here this y plus half the width of this section, half d by 2 minus y. So the height or width, height of this section is equal to d by 2 minus y, and its half will add to the distance of y, which is from the central line to the end of this section, will give you a value of y bar itself. Now, substituting this value of a and y, substituting this value of a and value of y in the equation of stresses, then what we'll have, we know tau is equal to f into a multiplied by y bar divided by I into b. B is the width of the beam here, width of the flange itself. So we put the value of f, which is known to us, put the value of a, which is equal to b into y h by 2 minus y plus multiplied by y multiplied by y bar. Y bar is equal to y plus half into d by 2 minus y itself, divided by I into b. I is the moment of inertia of the beam, full section, and b is the width of the section. This is the top section. So f divided by 2i d square by 4 is equal to y square. After simplification of this thing, it will reach here. Now we know that tau increases as y decreases. We see that the variation of tau with respect to y is a parabolic curve here also. And at the upper edge of the flange, where y is equal to d by 2 here, y equal to d by 2, if we put the value of d by 2 here, then the shear stress will become 0. And at the lowest end of the flange, where y is equal to d by 2, means somewhere here, at the lowest end of the flange is here, where y distance from this to this is equal to this, means y is equal to d by 2. Then the shear stress will become f by I d square by 4 minus small d square by 2 whole square. Or the situation reduces to f by 8i divided by d square minus small d square. Now let us consider a portion of I beam where y is less than d by 2, means distance from the central axis or neutral axis of the considered section is less than d by 2 itself, or y is we are designating y is a distance of neutral axis from the lowermost section line or lowermost fiber of the section itself, that is equal to jk. Here this y is less than the half of the depth of the flange, means y lies somewhere here, not here, not here, or not even not here. Now, in case of the value of a into y bar for the flange, but first we have to find out the value of a bar of the flange for this portion. Next, we have to add it with the a into y bar of the flange of this section itself. Means we have to multiply by the area multiplied by the distance of the CG of the section from the neutral axis itself. So the value of the flange itself, what is B, is equal to width of the B, area is width of the B, capital D by 2 minus small d by 2. That is d by 2 minus d by 2 multiplied by y dash, which is first of all d by 2 itself plus half of this depth, that is d by 2 minus capital D by 2 minus small d by 2 multiplied by half. So this is the from this distance d by 2 and plus half of this height equal to that distance equal to the distance of y, d by 2 plus half d by 2 minus 2 minus y by 2. So if we simplify, we'll have this is equal to this a into y for the flange is equal to b multiplied by d square minus small d square divided by 8. Now let us go for the wave itself. The value of the value of a into y for the wave above AB is equal to b into d divided by 2 minus y, which is like this, where b is the width of this wave and d by 2 is the depth, half of the depth of this wave. And if we reduce or subtract, if we subtract the distance of jk from y, from the neutral axis, which is equal to y, this will become to have b into d by 2 minus y. So the area of this portion from the flange to the end of this section is given by b into d by 2 minus y, and y bar of this section will be distance from the neutral axis to the CG of this small portion. So this will be half d by 2 minus y so this will be equal to half d by 2 plus y. D by 2 is the half of the length plus addition of plus with addition divided by half and both. So that is y plus half d by 2 by minus y, which means this is the y plus we are adding d by 2 minus y. D by 2 is the length for the full length minus the y, the distance of jk from the neutral axis, d by 2 minus y, and the section should be its half. So we have to multiply by half itself. So after minimizing, the equation becomes half d by 2 minus y, d by 2 plus y, or d by 2 d square by 4 minus y square. So this is the value of the wave above by b. And this is the value of the AY, value of the wave, it is the AY for the wave above AB, and this is the AY for the flange itself. So now if we add them together to get the total Y, so you have to add this one plus this one. So this you can b into d square minus d square by 8 plus d by 2 minus d by 2 into d square by 4 minus y square itself. Now we have got y bar. Now we can substitute this value of y bar in the equation of a shear stress on the layer at a distance y from the neutral axis, that is F into A into y bar we have calculated, and I into B. That's this portion is equal to this portion. So we are putting it here divided by IB, or FIB is equal to this plus this y square must be y square itself. We also see that here the tau increases as y decreases. Means distance of the CG of any section, if it reduce and closer goes closer and closer to the internal axis, so that we'll get y tau is also more than that. If we put as neutral axis where y is equal to 0, the shear stress is maximum itself. So let us see how will it impacts arc. Maximum shear stress tau max is equal to F by IB into d by 8 plus multiply d square minus y square into b d square by 8, while we are substituting y is equal to 0 itself. The shear stress at the bottom of the junction of the top of the wave and the flange, bottom of the flange is itself, that is at the junction of the top of the wave and bottom of the flange. So we have to put y is equal to d by 2 here. It is exactly the junction of the wave and the top of the and the bottom of the flange itself. So we have to put d by 2 here. Then we'll get the stress will be F minus IB d by 2 and d square minus d square, or F by 8i is equal to b by d d square minus d square itself. Now we see that the shear stress at the junction of the wave of the flange is different from the above expressions, where is y is equal to d by 2 and y is equal to minus 2, but at the junction where y is equal to d by 2, that carries a different portion. We also see that it carries different value. We see that the shear stress changes abruptly from F minus 8i d square d4 to F by 8i d by 2 d square minus d square. This shear stress at this junction suddenly increases by thus b divided by b times. So this portion is equal to this portion, but only additional portion is b by b. So the shear stress we can safely that if we multiply the shear stress with this portion with b by b, we'll get this maximum shear stress at the junction. Now, if I section is symmetrical like this, shear stress distribution will also be symmetrical. But if it is not symmetrical, shear stress distribution may not be symmetrical itself. From the shear stress distribution diagram, we see that the most of the shear stress is taken up by the wave. It is important factor in the design and various important factors, because we see the maximum shear stress is created on the wave itself, not on the flange. So we have to take into consideration of that to take the proper importance to the it. Now, distribution, there is another type of section we will consider, that is the shearing stress over a T section. The procedure for determining the distribution of shear stress over T section is same as discussed. But in this case, hence the section is not symmetrical about y-axis, therefore shear stress distribution diagram will not be symmetrical. For the section I, the section is symmetrical. We have two flanges at top and bottom and one wave. But T section, you know, there we have only one flanges and only one T. So stress distribution will not be symmetrical, will not be same. It will be a bit different. We have to find that. No. Now what we have here, a T-shaped section here, whose dimension is given. The width of the flange is 200, depth of the flange is 50 only, length of the wave is 500, and width of the wave is 50. And the moment of inertia about this horizontal axis is given by, just 1 second. that is 113. It's given by 113.4 into 10 to the power 6. So I is given here. First, let us find out the position of the neutral axis itself. We have to know that distance between the CG of the section and neutral axis is given by distance between the center of gravity of the section and the bottom of the wave is, which this is the bottom of the wave, this is wave, this is the bottom of the wave. And we have to find out the distance between the CG of the section and from the bottom of the wave. What is the center of gravity section? What is this distance? From this line, we have to calculate now. So what we are doing here, 200 into 50 into 225, 200 multiplied by 50 into 225 means 200 plus half of this distance is 225. Means the center of this center line of this section of the flange is away from this bottom lower portion by 200 plus 25. So the area is 200 multiplied by 50, and the area of the flange is also wave is also equal to 200 multiplied by 50, where length is 200 and 200 width is 50, and its distance of its CG is equal to 100. Distance half of this depth of the wave, which is equal to 100. So area multiplied by the distance, area multiplied by the distance divided by the area itself. This 200 multiplied by 50 divided by 200 multiplied by 50. This is equal to, there's few mistakes here. It should be 200 and this is exactly given. It should be written here. It was my fault. So y bar is equal to 162.5 millimeter itself. Now distance from the center of gravity of the certain section is distance between CG of the section and top of the flange is 200 plus 50 minus 162.5 is 87.5 itself. So how we have get it? We know that the CG is away by 162.5 from the lower end. So somewhere here. The total length is 200 plus 50. So if we subtract this length, we'll get the distance of that CG from topmost layer. So that will be equal to 200 plus 50 minus 162.5 is equal to 87.5 millimeters itself. We know that the shear stress at the top of the flange is 0. But now let us find out the shear stress at the junction of the flange and wave by considering the area of the flange of the section. And we know that the area of the upper flange is A multiplied by A is equal to 200 into 50 is equal to 10,000. And y bar 87.5 from the distance of CG from the top bar minus 50 by 2, half of the distance of the flange itself. That is 50 is the length distance of the flange divided by 2 is 25. So y bar distance of the CG of this concerned upper flange from the neutral axis is equal to 62.5 millimeter. So width is given as of the flange is given as 200 millimeter. So value of A, y bar, I and B in this equation, which is where A, F is given, I is given. We have calculated A and we have calculated Y. So y bar and B. So we know the value of B. So this thing will take, equation will take this particular shape. And the numerical value will equals to 2.76 MPa. So the stress at the junction of the flange and wave is given by 2.76 MPa. But we can also calculate this thing at the considering the area of the wave. of the section. How can you do it? That the area of the web means the vertical portion of the section, that's 200 into 50. Y bar is 162 minus 200 into 2. The distance of the center of the web, distance of the center of this wavelength from the neutral axis is, that is neutral axis from the bottom line of the wave is 162, and if we subtract the length of the wave, half of the length of the wave is 62.5. So we have already given for the wave is 50 millimeter. So shear force at the junction of the wave, FIB, I is given, A is given, and the F is equal to distance of the bottom portion of the line, that is 62.5. And we put the value, so that is equal to 11.04. Now we put this at the junction suddenly increases from 11.04 to 2 ampere is equal to 2.76 ampere. So we are getting two values of the shear force at the junction, because thus we'll see that it will increase from 2.76 to 11.4. Now find out the shear stress at the neutral axis, where the shear stress is supposed to be maximum. Consider the wave positive section. So consider the area of the T section above the neutral axis. We'll know that A, the area of the top portion into 62.5, the portion above the length, height of the portion above the height of the portion of the wave above the neutral axis, above the neutral axis, that is 37.5. We have already calculated, multiplied the width W, multiplied by 37.5 divided by 2. So that becomes 660.2 into 10 to the power 3 millimeter cube. And is equal to 50 millimeter. So maximum shear stress is equal to tau max. You put the value of F, you put the value of A into Y is equal to this 62 and this, and divide by I and divide by width. 50 is the width. So the maximum shear stress value will be equal to 11.64 ampere. This shear stress distribution we have shown in the diagram itself.